Okay, so last time we talked about the complex power series. And many concept ideas can be carried over from the freshman calculus. So we introduced the complex sequences and complex series. And what do I mean by a series converges absolutely? And also we discussed the power series, and we also had the radius of convergence. And every power series has a radius convergence between 0 to infinity. And that means if your point of interest, the distance between the center of the power series and the point of interest is less than the radius of convergence, then your power series converges absolutely. And otherwise, well, if the z minus z0, the distance between z and z0 is greater than the radius convergence, then your power series should diverge. So that was the idea. The question is, then how can I find such a radius of convergence? Radius of convergence, well, can be found by using the ratio test. So this thing we also discussed from our previous class. So if R equals to 0, then the radius convergence, well, suppose that the limit of this number exists. And so if there is such a number, then, well, R must be greater than or equals to 0. And if R equals to 0, then we say the radius convergence is infinity. So in other words, your power series converges for all complex numbers. And if R equals to infinity, then that means the radius convergence equals to 0. In other words, your power series only converges at the center of the power series. And otherwise, if R is some number between 0 and infinity, then your radius convergence is just 1 over L, the reciprocal of L. So how do I know that? Yeah, this is not horribly complicated exercise. Well, I guess you can easily convince the theorem of the proof of the theorem. So let us just take this for granted, and we will move on to the next section, which is 15.3. The functions given by power series. Okay, so why do we even care about the power series? So the same reason as we did in the calculus. So in calculus, we studied power series just in order to compute some transcendental functions. Well, because there are many interesting functions other than the polynomials and rational functions. Like, for instance, if you want to compute some interesting functions like the exponential functions and sine and cosine functions, and many functions are only defined by using the power series. And same is true for the complex analysis. So interesting functions can be defined by using the power series. So power series is actually a function. It's a function of the variable z. And in today's lecture, I want to discuss the main interesting properties for the functions given by the power series. For instance, we can discuss about the continuity of the function of power series and the differentiability of the power series and so on. All right. So, well, suppose we have a power series. And from n0 to infinity, a n z minus z0 to the n. For future purpose, I'm going to give this guy a name. I will say S of z. This number exists if and only if z is the radius. So z is in the radius of convergence. So this is clearly this is the radius of convergence. So this is the function of z. But as a motor human being, so we cannot compute this infinite series. So therefore, we somehow need to truncate this infinite series. So the truncated series, I would say as n of z. So defined by the first n terms of this power series from n0 to n minus 1, a n z minus z0 to the nth. So this is just this is a polynomial of degree n minus 1, right? And well, since this is the function and this is the approximation, so speaking of approximation, then we also always need to consider the difference between the true function and the approximation, which will be called as an error or remainder. And rho n of z, which is defined by the s minus Sn of z. So, well, always we say the z is in the radius of convergence. Okay, so, well, since we are assuming that this guy, z, is in the radius of convergence of this power series, so therefore, the power series convergent. If and only if, by definition, the partial sum sequence S and Z is converges to SZ, and if and only if this remainder, the sequence of remainder, converges to 0, right? And speaking of so this is a sequence and which converges to 0. So, well, in other words, using the epsilon and Rn argument. So in other words, I say for every positive epsilon, so I must be able to find some integral number, integer, and epsilon such that if n is greater than epsilon, then this guy converges, is less than epsilon. Yeah. So this is our epsilon delta, not delta, epsilon and n definition of the convergence of the series, sequence. Okay, so but I also want to emphasize that this convergence of the partial sum sequence to the function s of z should be understood as not a convergence of a single number, but you should consider this as a convergence of a function, right? So Sn should be considered as a sequence of functions. And in order to discuss this convergence of the sequence of function, the pointwise continuity is not a good choice. There is actually better definition that can be used for the convergence of the sequence of functions. Do you know what it is? Uniform convergence. Yeah. Right. So today I want to discuss about the uniform convergence of the sequence of functions. The definition is this. If Fn is a sequence of functions on the domain D. So this means, well, every term in this sequence has the same domain, right? This is so you should consider this subset as a common domain of each of these terms in the sequence. Then we say, then this guy converges uniformly to function f on D if for all epsilon you must be able to find some integral number n such that if n is greater than epsilon, then f of z minus f of z1, minus f of z2 is less than epsilon for all z1 and z2 in D. So the point is, so yeah, most of you are very well aware of the notion of the uniform convergence, but let me emphasize just one last time. So the point here is this whole number n can be chosen independently from the position of these 2 points in the domain D, right? So if you can find such a nice number n independent from z1 and z2, then we say that for this convergence is uniform, right? Okay, so is it something to do with our power series? Yes, absolutely. This is the first theorem that we try to prove for today's lecture. Well, suppose I have chosen any random point inside the circle of the convergence. Of a power series. An z minus z 0 to infinity. Then the series converges uniformly. Well, if you want to discuss something about the uniform convergence, then you must be clear about the common domain of this sequence of functions. In this case, common domain is 제가 뭐 실수를 했나요? 잠깐만요. 제가 실수를 Thank you. 그렇죠. 그렇죠. 예. 죄송합니다. Thank you for pointing this out. Yeah, that was really stupid mistake. Yeah. All right, so coming back to the uniform convergence of series, and the series converges uniformly in the disk. Which disk? Okay, so what does it mean? First, so since we are talking about the uniform convergence first I will need to make sure that what is my sequence of functions. In this case, my sequence of functions is just nothing but the partial sum sequence. Partial sum sequence, and the common domain that we are talking here is this closed disk. So, well, as you can see from this picture, so Z1 is the point inside of the radius convergence. Therefore, this closed disk is slightly smaller than the circle of the convergence, right? And so, well, and I say this convergence is uniform in this closed disk. Okay. Okay, so what is the idea? So the main idea to prove this is the absolute convergence of this power series. Well, I hope you remembered, or you all remember this. And my point Z1 has been chosen inside of this radius circle of convergence. Sorry. This is, I define this guy to be R1, and this is less than R. So, and you have to remember, if this guy was chosen from inside the radius circle of convergence, and if you plug in this guy into here, then this series converges absolutely, right? So absolute convergence, that means Z1 minus Z0 from 0 to infinity, this guy should convergent. Okay, so this guy convergence means for any epsilon, I must be able to find some integer and epsilon such that if the index n is greater than this n over epsilon, then so oops. Oh, sorry. I also missed the power here. Should be less than epsilon. Well, so the partial sum sequence here is from the summation from n0 to n minus 1. Therefore, yeah, the difference between the limit and the partial sum sequence is precisely this guy. So yeah. So well, I am repeating the definition of the absolute convergence. I'm gonna say this. I'm gonna call this guy to be sigma of n. Okay. Now, just let me choose any random point from the similar circle, R1. So yeah, so this is the point from the distance between this point and the center of the power series is slightly smaller than the radius of convergence. Now, this is the remainder, which is ANZ minus Z0 to the n, but clearly this guy is bigger than the previous one. And well, I can break down this one into these two. But what if I replace this guy by Z1? Yeah, this is, we're comparing this and that. This is slightly bigger, greater than equals to this guy, all right? So this is bigger than this. And this is what? this is precisely the sigma n that I mentioned before, and this is guaranteed to be less than epsilon if sorry. Yeah. So if n is an epsilon, then this remainder is always less than epsilon. And here the point is this choice of an epsilon is completely independent from the choice of this point, from this smaller circle. So because of this reason, so since I was able to choose this guy, independent from the choice of the point z, so this convergence is guaranteed to be uniform inside of this closed disk. Okay, so this is our first theorem. And the next theorem is about the continuity of this function, the continuity of the function given by the power series. So yeah, for simplicity, please allow me to call this guy S of z. And I say this function is continuous at each point inside of the circle of convergence. So our function defined by power series is always continuous. All right, let me prove that. First, we choose any point. I would say z from inside of the circle of convergence. So well, and I wanna say that this function, I wanna claim that this function S of z is continuous at this point z, z1. To do that, so for any epsilon, I should find some positive number delta such that if z minus z1 is less than delta, then the distance between is less than epsilon. Okay, so my goal is to find such a nice delta. Okay, so let me try to find this. Beforehand, yeah, I will play a little trick here. Well, so we said this is the remainder. The remainder was defined by the Sz minus the partial sum Sn of z. So in other words, S of z is Snz plus the remainder, yeah, which is so obvious. But now this expression, please allow me to replace each of these S of z by this expression. Then as z minus as z1 is SNZ plus log n of z, and everything minus SNZ1 minus log n of z1. So and using the triangle inequality, I get this. Okay. Now I am ready to do some analysis here. Well, first, so let me focus on these first two terms. First terms, Sn minus Snz1. So what is Sn? Sn is merely a polynomial, so which is guaranteed to be continuous, right? So Sn is a polynomial. So which is always continuous. So for any n, I must be able to find some delta, which is so small, so that the difference between this guy and that guy is less than epsilon. Okay. Okay, which is good. On the other hand, now I need to find some bounds for these two remainders. How can I do that? First, let me try to find the bound of this guy first. We choose a number, which I will say R0. And I want this guy to be less than the radius of convergence of the original power series, but greater than this point, the greater than the distance from the center of the power series and this point. Okay, so to be, so I want this guy to be such that we less than the radius convergence, but I want this guy to be greater than so in picture, so this one should look like this. This is the center of the power series, and this is the radius of convergence, and this is my point Z1, and all right. I'm going to change. I'm going to say this is R0, right? Yeah. Okay. So, in this case, suppose that my Z is inside of this red circle here. And this is clearly this red circle, this distance from the center of this distance, R0, is clearly less than the radius of convergence. Therefore, every point inside of this circle will make my power series converges absolutely, right? And because of previous argument, we know that if Z is z minus z0 is less than r0, then for any epsilon, I can find a number and epsilon such that if n is greater than this number, then the remainder is less than epsilon. Okay, good. Now I want to use the fact that Sn is polynomial, so therefore each must be continuous. So, and Sn is polynomial for all index n. So therefore, instead of choosing just any random index n here, I'm going to say this index to be a number index which is guaranteed to be greater than this number here over here. So please allow me to set my index n is n sub epsilon. Here, n sub epsilon is the number that I have just found over here. And I want this guy to be greater than this number, so I'll just say, just put +1 over here. Then, Sn is continuous. So therefore, for this specific index, n epsilon +1, I can find a delta which is so small such that Snz minus Snz1 is less than epsilon if z minus z1 is less than delta. Well, here I was saying a little bit ambiguous over here. So I said the delta should be small, but how small it should be? So I require my delta to be so small that this distance, this distance z1, z from z1 is completely contained in this red circle. So I require that delta to be this much small. So and likewise, so well, if my delta is this small, then every z inside of this circle must be also guaranteed to be and by the same argument, so this guy is also less than epsilon. So okay, let me combine all these three inequalities here. So this is less than epsilon, and this is also less than epsilon, and this is also less than epsilon. Therefore, if z minus z1 is less than this delta, then which is less than 3 times epsilon. So the proof is done. Okay, great. All right. So this is about the continuity of the function given by the power series. And now we will turn to the integration and the differentiation of the power series, the function given by power series. So again, so I want to remind you the fact that we have been using in the freshman calculus. So suppose that we have a function given by power series. And is it differentiable? Yes, it was. And how did it, do you remember how we differentiated of such a function? So we actually use the trick so-called the term-by-term integration and the term-by-term differentiation, right? And same thing is also true for in the complex analysis. So if you have a function given by power series, and if you integrate or differentiate each of these terms, and you know how to differentiate, how to integrate or differentiate each of these terms, because a single term given the power series is just merely polynomial. So being able to differentiate or integrate polynomial will also give you the idea how to find a function, the differentiation and the integration of given power function given by the power series. So that is the idea. So first, I want to discuss the integration of function given by the power series. Suppose that I have a curve, and I require that this function, this curve is interior to the circle of the convergence. And let me say g of z is any function that is, since we are talking about the integration, so we require that this guy to be just merely continuous on this curve C. Then we have this. So since, well, because of the previous theorem, so we know that this guy is continuous everywhere inside of the circle of convergence, right? And this continuous function has been multiplied by another continuous function. And we are talking about the complex line integral of this guy. And so, well, in other words, I just want to emphasize that this was actually the power infinite series. And the result of this theorem is, if you integrate this, which is the same as the continuous function multiplied by each of these terms. So, what do you know here? So, well, as long as my curve lies inside of the circle of convergence, then this infinite sum and this integral, these two operators, they are actually interchangeable, right? And well, and I claim this theorem actually proves the term-by-term integration. Why? Just put the g of z equals to 1, constant, identically one function. Constant, if this guy equals to constant one function, then this actually tells us the justifies the term-by-term integration, right? Okay. So, well, again, we're going to use S of z. I'm going to break down the S of z as a sum of the partial sum sequence plus the remainder. And well, here for this integrand, we multiply this guy by g of z. So g of z over here and gz Sn of z plus GZ. So okay, let me talk about these functions. And this was continuous, and this is continuous. This is continuous, and this is a polynomial. So this is automatically continuous, and this is also continuous. So these two guys are continuous functions on this curve C. Therefore, this g of z times the remainder, this function also must be continuous on this curve C. So, well, talking about the integral of this guy is completely okay, justifiable. So, well, I want to put this integral sign to the both sides of this equation. So this is what this is this, and the integral of this guy. Well, hold on. So this is just a polynomial of degree n minus 1. So please allow me to instead of writing like this, allow me to write this guy using the summation. But this is a finite summation. So an times the integral g of z and times z minus z0 n by dz and plus the integral of the remainder. Okay, good. Okay, so what I want to do is, as n goes to infinity, I want to show that this guy tends to 0. How can I do that? Maybe by using the ML inequality, I guess. Yeah. So now, let me say that m is the maximum value of the modulus of this function on this curve. Yeah, this number is guaranteed to exist because, well, we know that this function is continuous, so this number should exist. And, well, also LB, the length of the curve. Okay, so now we know the bound of this guy, but what about the bound of this guy? Well, bound of this guy is also, well, can also be found because why? Because this curve C this guy is known to be lies completely inside of the circle of radius, circle of convergence. So therefore, this Z must be always inside the circle of convergence. And if Z is inside the circle of convergence, then, well, as this index n is getting sufficiently large enough, then this guy is guaranteed to be, the modulus of this guy can be suppressed sufficiently small enough, right? So also, we know that there is a integer and epsilon, which is independent from Z, such that if n is greater than an epsilon, then is less than epsilon, right? So now we are ready to discuss the maximum modulus of this complex integral. So, well, by using the ML inequality, this the maximum modulus of this is m, and the maximum modulus of this is epsilon. So m epsilon times the length of the curve, which is L. Okay, so well, yeah, of course, this is true. Well, the index n is greater than an epsilon. So What now? So, well, that means independent from the choice of the point z here, but this guy is tends to 0 as n goes to infinity, right? So as n goes to infinity, so must be 0. Okay. So, well, so n goes to infinity, so that means, so therefore, we have this. Oh. And we have this result. Okay, great. So, well, so this proves the term by term integration. All right. So, well, so this is actually turns out to be very interesting and useful theorem that we can take use of. So if letting g equals to 1, then this side, if g equals to 1, then this integral is merely z minus z and dz. So this justifies the term by term integration. And actually, I can do even more than that. Why? Well, here, okay, let me just go back to the theorem. So I said I chose C to be just any curve that is in the circle of convergence. What if I choose this guy, C, to be not just a curve, but a closed curve? Yeah, then this makes things more interesting. So if on top of that, so assume that C is a closed curve, then S sub Z is just summation of, oh, sorry, I forgot dz. Z to infinity and an and z minus z0 to the n dz. Okay, well, since we are assuming that C to be a closed curve, and this is what? This is just an analytic function. And if you take a closed curve integral over the inner analytic function, then the answer must be automatically 0, right? So this guy equals to 0, so everything equals to 0. For the right-hand side, so this guy equals to 0, right? So I was able to get very striking result out of this term by term integration theorem. So what does it tell us? It tells us that the function given by the power series is automatically analytic, right? Do you know the Morales theorem? So what is the statement of the Morales theorem? Suppose that you have some mysterious function lying over some mysterious domain, but if the if the integral of the function over any closed curve in the domain equals to 0, then that implies your mysterious function, it must be analytic on the domain. And since, what do we have here? This function is already always the integral of this function over any closed curve equals to 0 implies that S of Z must be analytic on this circle of the convergence. Okay. So this result is assumed to be very important. So it deserves a corollary. I have a function given by the power series is analytic at each point inside of the circle of convergence. So if you have your textbook, then I strongly recommend you to read the section 15.3. So well, this proof is slightly different from the approach that is given by the Professor Krasik. So this our textbook gives us different proof for the analyticity of the function given by power series. They actually try to give you more direct and definition-driven proof in the proof of the analyticity of the function given by the power series. And this is somehow indirect approach to prove the analyticity of the function given by the power series. Which one is better? I don't know. Well, but however, you're a student, you should be able to know both of them. So this is the reason that why I am recommending you to read the proof given that is given in our text. But yeah, so this is very important result. Every power function given by the power series is always analytic inside the circle of the convergence. Okay, this is nice. And what's next? Since we have done about the term-by-term integration, so naturally, the next theorem should be about the term-by-term differentiation, right? I have a power series, function given by the power series. And this guy can be differentiated term by term. So that is, so S prime Z is from 1 to infinity, n times an z minus z n minus. Yeah, so this is precisely the same as, again, the same as the theorem that we studied in the freshman calculus. All right, let's prove this. So first, I want to define, so I will try to prove this by using the Cauchy's integral formula. And in order to make use of the Cauchy integral formula, first I will need to specify which curve that I am working on. So, well, this is the center of the power series, Z0, and this is the radius of a convergence of this power series. And well, just choose any random point here. So any point inside the circle, circle of convergence, and I want to take a small closed curve here first, and I require that this curve should be oriented counterclockwise, and I also require that this curve should be lying completely inside of this circle of convergence. And I'm going to call this curve to be C. Okay, now my curve has been chosen, and I want to define a function, which I will say g of s is 1 over 2 pi times I and times s minus z everything squared. Okay. Now I will try to make use of this previous theorem, this guy. And I'm going to put my function, I'm going to replace my function g in the place of this function g over here. So I have defined this function, and this function is clearly continuous on every point on this curve C, right? So since g is continuous on C, gs and s of small s ds is what? 1 over 2 pi times I integral s of s by s minus z everything squared and dz. Sorry, not dz, ds. Okay. Can you recognize this expression? Yeah, this is clearly s prime of z because of the Cauchy's integral formula, right? Okay. What about the other side? And because of our previous theorem, we know that this number should be, this guy should be from n0 to infinity, an times c gs times s minus z 0 to the n ds. Am I right? Yeah. Okay. And this is what? This is 1 over 2 pi times I c s minus z0 to the n over s minus z squared and ds. Well, again, by using the Cauchy's integral formula. So this one can be understood as the derivative of the function z minus z0 to the nth, the derivative of this guy by z, right? And yeah, I think this proves the theorem. So this is the summation and the coefficient, they just carry over times the dz and z minus z0 and n. Okay, so s prime of z is just turns out to be this guy. So this justifies the term by term differentiation. Okay, yeah, great. Okay, so now we know. So since we know that this, so also we know that because of the geometric series, we know that this geometric series is converging to this guy. So therefore, we are free to find the power series of the derivative of this function or the integration of this function by using the term by term integration and term by term differentiation. Yeah, which is precisely the same exercise that was done in the freshman calculus. So I won't spend another time to prove this. So, all right, okay. Turning to the next section. Now we are on the Taylor and the Maclaurin series. As you might have guessed, so every theorem, every statement is pretty much analogous to the freshman calculus. And this is no exception. Well, since we are studying the Taylor series, but well, you know what I mean. So the expression is, in terms of the expression, they are precisely the same as the freshman calculus. Suppose that I have an analytic function, a function f is analytic on a disk. Then this function has a power series representation. Well, an is the nth derivative of f evaluated at the center of the series divided by n factorial. Okay, well, so if you look at this formula or this expression, then you can easily recognize that you have seen this before in the freshman calculus. The expression is precisely the same as the freshman calculus. But there is one crucial difference. Can you recognize that? Well, in freshman calculus, even though your function is infinitely differentiable, but there was no guarantee that your Taylor series of your function converges to the original function, right? Being able to infinitely differentiable does not guarantee the Taylor series of that guy is actually the original function. But however, in our case, if my function is analytic, then, well, being analytic actually implies that means automatically means that your function is infinitely differentiable. And in this case, it has the Taylor series, and the Taylor series is guaranteed to converge it to original function in this radius of convergence. Right? This is the crucial difference. So although the statement sounds like a very local statement, so well, it feels like that in order to make use of this theorem, then first I will need to make sure that my function is analytic on some open disk, but this condition may be dropped because, well, being analytic, your function being analytic is automatically already a local statement. Why? Because suppose that your function is analytic at some point. That means your function, well, you can find some epsilon neighborhood of that point, and on that epsilon neighborhood, you know that your function is always analytic in that epsilon neighborhood of the point. So, well, actually, so therefore, analytic on the disk, this condition may or may not be dropped. Well, that's a psychological reason, but I just put it over here. Okay. Well, and choice of this radius of convergence, well, actually depends on the domain of your function f. Well, if your function is entire function, then well, you can choose your r to be any arbitrary large number. But if you're if your function f is some singularity at some certain point, then that somehow restrict the maximum number of your radius of convergence. Well, we'll come back to this issue later. But however, first I'm going to try to prove this theorem. Oh, by the way, so this guy. We say the Taylor series of function f at z0, and if your Taylor series, if the center of your Taylor series turns out to be the origin of the complex plane, then we say that is a Maclaurin series. All right, so I will prove this, and without losing too much generality. So I'm gonna say my z equals to 0. Z0 equals to 0. We choose any z from the disk z minus z0. So inside of this circle of radius, so circle of convergence. And let me say this radius is the distance between the center of the power series to the point. I'm going to say that is r. And I want to choose another number, which I will call r0, such that greater than r and less than large r. And C0 is a positively oriented circle whose radius from the center is precisely r0. So, okay. I will begin from the Cauchy's integral formula. The C0. So you have to remember, you should be able to imagine that this curve that I'm mentioning over here is a somewhere between the z and the radius of convergence of the power series. Yeah. And due to the Cauchy's integral formula, so this guy should be like this, right? Now I'm gonna play a little trick over here. S minus z is just 1 over s times 1 over z over s. And we also know that 1 over 1 minus z is n minus 1 and 0 to zn plus zn. This is just simple, the high school algebra. So you should be able to understand this. Yeah, okay. Yeah, of course, z must be a number other than 1. All right, so I'm gonna make use of this formula for onto this fraction. So s minus z is 1 over s. This guy, now my z is just z over s. So 1 over s now carries over, but this summation s over z to the n and 0 and n minus 1 plus z over s, everything to n to the nth and z over s. Okay, so summation from 0 to not infinity, yes, n minus 1 and z n s n plus 1, right? And plus, yeah, I'm gonna put the z to the nth in front of this ugly fraction. And if I multiply this s to this denominator, so I get s minus, I restore s minus z and everything by s to the nth. Okay, good. All right. Okay, so now I want to compute this integration right over here. So C0 f of s ds s minus c. Oh, one thing that I will need to make sure, that is what is that? So, well, this is r0, and the distance from the 0 to the z, it was r. Therefore, this guy, this number is, the modulus of this number is less than 1, right? Because this point S is assumed to be the point on this circle C0, right? And you know, R0 is greater than R, so therefore the modulus of this number is always guaranteed to be less than 1, right? Okay, good. So integral over oh, sorry. From n0 to n minus 1, fs ds as n plus 1, and since this z is nothing to do with variable s, so I can it is safe to say I can get this guy out of this integration, and plus, well, this is just constant, so z to the nth integral is 0, f of s and s minus z to the s to the nth, and everything ds. Okay, all right. And well, this is just a finite summation. So in this case, this summation can be safely taken out of this integration. So C0 fs ds and Sn plus 1 and everything by Zn, and this guy carries over. Okay, now what? I have seen this guy before. So this is because of the Cauchy's integral formula. So this is 2 pi I C0 fs ds, and Sn plus 1 is Fn 0, everything by n factorial. So, well, okay, I somehow messed up my notations, yeah, because I just forgot to bring this fraction over here. But if I multiply this fraction into each of these guys, then I have, well, by putting this 1 over 2 pi I over here, then this is just f of z. And the next summation is from 0 to n minus 1, fn 0 to the n factorial plus sorry, yeah, I already know that I just ran out of time, but just giving me just one more minute. Thank you. And I want to claim that this guy tends to 0. How? Well, because I want to consider the modulus of this number, and by the triangle inequality, this is which is less than this, and S is assumed to be the point on the C0. So therefore, the modulus of this guy is always R0, and the modulus of Z was assumed to be R. So this is this. And well, if f is the maximum modulus of this guy, this function on this curve is m. Yeah, is m. If m is the maximum modulus of fs on C0, then this guy is, yeah, I mean here I'm using the ML inequality. So the modulus of this guy is R. So Rn over 2 pi times m times R0 minus R times Rn times 2. Well, the length of the curve is 2 pi and R0. And this is m R0 minus R times R over R0, everything to the n. And since this guy is less than 0, so this guy tends to 0 as n goes to infinity. Okay. I really appreciate your patience and see you next time. Thank you.